Okay, welcome back to class 10, and this is video 3, and in the previous video I talked about mesh refinement and how we could converge to a solution, and in many cases some scenarios won't converge. We could actually have a really hard corner that creates a singularity which sends meshing up into the atmosphere. So let's talk about a little bit about that, mesh results, right? So one of the big problems with the computer is it really gives you a sense that this is the answer in finite element analysis. That okay, because it's a pretty little plot right there. But you can plug any numbers into this calculator, even an art major. Sorry, I had to pick on you. Even an art major can learn to operate the calculator and stick numbers in and hit equals, even though my calculator doesn't have an equals button on it. And it'll give an answer. That's the same thing here. Like, you can learn how to run the machine, and we could just give it to anybody. You don't need a mechanical engineering degree to run FEA. Anybody can do it. Anybody can learn to do it. But if you do the thing wrong, if you don't know what's going on, if you pick the wrong boundary conditions and so forth, or if you don't have some idea of the limitations, you could have very wrong results. And there's a really good quote in the beginning of one of my books, and I can't find it, but it says something to the effect, and I gotta find this, I'm gonna give proper attribution, that the FEA has allowed us to be wrong with more certainty than ever before, right? So that we can be completely wrong, but we should be very sure of ourselves, right? Because we have this solution. And one of them is like these contour plots. They really look good, but if we don't know what the mesh is, right, we can be deceived. But one actually, and this is just a very simple thing that you might not realize, is that it solves at the nodes. It solves for a particular thing at each node, and then it averages all the way around and creates a contour plot, right? So like sometimes it's good to just take a look and see with a mesh plot and see these element answers, right? So you could see the change from one element to another. If it's very large, if you be careful of believing the information at a particular node. And I'll do a couple in Solidworks Simulation. Do a couple little probes, and you can kind of see, okay, this is the answer at a particular node. But be aware that your mesh density matters, but also because right here, what you're seeing right here, this is the node generated contour plot, right? But below is what the element plot would be. Now, you don't necessarily want to present this, but it is looking at it kind of give you some more information, right? So sources of FEA error, and I got this from this little blog right here from 2016, errors in FEA and singularities. And if you go to this link up there, you can find out this. So I just condensed right here. So modeling errors due to simplifications. So we try to model the real world, yet we're not able to do it 100%. We have to simplify. We can't put everything in the kitchen sink into our model, right? So we have to, and it's a good idea to simplify the thing, but we got to simplify it knowledgeably, right? So that could be modeling errors. So we use a wrong geometry for the thing, or the wrong definition of the material, right? The material might be more complex than what we have. I think this is one of the biggest ones because it's really actually difficult to find in a real world problem to get a really good estimate of what the load is going to be on something quite often. That right there is sort of you pick a scenario, and you might kind of go from the side and kind of say, well, it's probably going to be a dynamic load, so we'll do a static load equivalent of a certain amount and that kind of thing. The boundary conditions can really be different, but we'll run across this. I think one of the most common ones is when we have a simply supported beam, right? And so in SolidWorks, we're going to go ahead and use Solid.Elements for this, but there's kind of something you got to worry about in the bearings, right? Because if you just maybe cut off, make a little section right here, and we'll do something we'll call the split lines, and you just tell it to hold all the nodes right there. It's no longer simply supported. It's going to be fixed because it's going to grab each of these nodes and it's not going to allow them to displace. And so now, while you thought that you were going to get a simply supported reaction right here, you're actually going to get a fixed thing. The wrong type of analysis, like linear versus nonlinear. That's a big one here. The discretization errors right there. So I was talking about the mesh refinement, the size and the shape of the element. So skew matters, right? If you have a really narrow, thin triangle, very bad, right? Can be very bad. You want to try to keep them, and you want to transition from like a small element to the next size elements. They need to have like a certain amount of transition to them. So skew and sharp angle is very bad. The number of elements through the thickness of something matters, right? So if this is hollow, right? So let's see, let's get in there. This is hollow. We don't want just one element through the thickness. We would like actually 3 maybe, but sometimes that's just not possible, especially with those solid elements. So that's one of the reasons why plate elements are preferred for something that's thin, because we might not be able to, that plate or shell elements, we might not be able, it might just be the dimensions of the actual thing itself might be such that you can't mesh it with solid elements and get enough through the thickness of the part. So the element type for that application, that's an example where you might want to use a shell element. Numerical errors are also possible as well. Integration error, the wrong solver type for an application can come up. Round off error, I guess. I think that maybe should belong to numerical errors. But anyway, read this article for some more of those things. And there are a lot of different types of capabilities within Solidworks Simulation. I'm really just going to describe doing like simple static problems, but there's tutorials built into the Solidworks Simulation, so you're welcome to go look at them. You can do all kinds of different things. You can do analysis of an assembly. You can mix the elements types. This can really be a dangerous thing to go down, so you really need to be well informed if you're going to make a plate element attached to a solid element, and God forbid have a truss element in there as well. But you can do apply like non-uniform pressure on something. You can have contacts that are taking between place. So like, you have 2 pieces and they're not actually adjoined to each other. You can account for the fact that like they might separate a little bit as one piece stretches and the other piece isn't, like, they're not glued together. So we can do contact elements. That's an important type of thing to know about. You can also have large displacement. That's usually going to be a non-linear thing if the displacements get so large. Shrink fits, that's interesting. A lot of times I think we actually trick it by using temperatures to like either expand or contract the pieces. Remote loads, I don't know what that is. A trend tracker, I don't even know what that is, I'll tell you the truth. An analysis of sheet metal. There's a lot of other ones to go through, right? So maybe explore some that you might want to do. Just remember that this is a utility that you could be perhaps using for a capstone project in your senior year. But this is the one that the Solidworks Simulation that we use the most, and I think this is a really good idea to go through this tutorial and to learn about these basic things going through here. So I think I have used up enough time here. I have an ASME meeting in 13 minutes. I can do this one. All right, so I think I tried this one in class, but I made the mistake that it's actually steel. I actually did my analysis and the example based on steel. So in the previous class, I think we even did this one, and I showed you the results. So let's go ahead and do this one in SolidWorks Simulation here. So I will try to, let's see, I'll close this up here, make this bigger, and I'll close this guy down, and I don't need to save you. So in this part right here, I'm going to hit New, create a part, and so I'm going to do my typical SolidWorks thing, I always turn this off to plain. I like white background. So for this part right here, I'm gonna try to keep the X and the Y and the Z the same, right? So that's my strategy, and I'm gonna make this little L. I'll give it a little bit of a radius right there to make up for that. All right, so I'm gonna take my top plane and make a sketch. So and I forgot again, I need to make this metric, so I might as well get out of that and come over here and make that into millimeters by pulling that up. All right, great. I'll move you over the side so I can see what the time is. I'll go back and edit that sketch I started, and we'll make this 500 millimeters, 500 millimeters, boom. And this one was 300 millimeters, 300. And I'll put in a little bit of a fillet right there, and I'll go 50 right there. All right, so that making that decision could have an effect on what my results are. So it might be something I'm going to go back on and experiment with and see what are the effects of this modeling decision I just made. So I'll clear that up, and then I'm going to put on the right plane right here another sketch, and this thing is a 10. Did I do that wrong? I think I did it wrong. Yeah, I'm in the wrong thing. Get rid of that. Why did I do that wrong? I don't know. Should be in the right plane. There we go. Make a sketch. There you go. And I'm going to make a sketch right there, and I'm going to make it 10 millimeters, which is pretty thin. This is going to be pretty thin wire. Pretty much that the thing is made out of. So it's a little deceptive for what it looked like originally, right? So we're going to use that, right? So we had one of the sketches was the little piece. You can see the little circle onto that they're showing right there, and the other is the path, right? So we can accept that. So we're done with the modeling side of things. Now, unless you have you've already turned it on, you might need to come up to here and go to the add-ins. See the little gear at the top, and go to add-ins and turn SolidWorks Simulation on right here. And you might want to click on this one right here so it always comes on. But you might be using a lab computer, so you might have to do this every time. So we come into simulation, and we go to new study right here, hit this, and you can see there's all kinds of other things, but I think you can only turn them on. Actually, I don't even know why they're not available, to tell you the truth. I think you have to, I don't know. I think that maybe they should be available. Maybe I just have it onto just the static solver right now, but I hit OK, it's choose static. And now we want to go down this list. And I think I have another video where I'm actually teaching you how to do these things, but well, more is better, right? So we're going to go down this list, and the first one I'm going to go to the part and right-click it and apply material. Right? There's other choices, but obviously. So like I said, I made this steel. The thing you want to look for is the elastic modulus, right? There's lots of different steels, but the elastic modulus is really the important one. Poisson's ratio, a little important. The rest of these things don't really matter into what the results are going to be for this type of analysis. I mean, there might be a strength in there, but that doesn't really change what the strength is of the piece, right? It's just going to be often, you'll see it on the scale of the stresses. We're only going for displacement right here in this particular one. We'll be doing stresses soon, but right now we're just looking for displacements. So I'm going to pick my go-to ASTM 836. So it has 200 gigapascals is what that actually says right here. We can actually put that down here. Here you go. Here's megapascals. Here it is right there. So you can say that it's 200,000 megapascals. That's going to be, let's say that's good enough. I think in the problem I actually used 207, but I don't know if I have one in here that I can find that's 207. I could just start picking steels. There's a 205. That might get us closer to the thing. Might be more accurate. So here, let's go with the 205. I don't think, because of the nature of the way I have this installed, where I need admin privileges to be able to make changes, where I could actually create my own material, which would have been a nice thing to be allowed to do, but I don't have admin privileges, so I can't get into it. Anyway, I'm going to pick that. What did I pick that? No, I said I was going to pick the 205. Let's pick the 205. So I picked the 4130 steel, and I hit apply. It doesn't go away, so just note, make sure you see that next to the part right there that it says what that is. Connections aren't necessary in this one because they're really for when you do assemblies, and they talk about the connections between parts and assemblies, so we don't need it. So we go down to fixtures and right click, and there's different choices, and these are the boundary conditions, right? So I'm going to hit a fixed geometry, and there are more advanced options onto here, but I'm just going to grab a hold of this face right there, and it gives you a little preview of what that looks like. And I'm hit OK, and then I'm going to hit, so I'm okay with my boundary condition. Now I'm going to hit loads, and I'm going to hit a force, right? And you can see there's other types of loads that we could put onto this. And I'm going to hit it onto this. Now the default is just to make it perpendicular, but we need to actually make it go downwards. So we want select direction, and now we're going to need another surface to define what the directions are. So we could use that same, right? So I use that face 1 for both the location of where the force is going to be and to define the direction. And this is SI, so that's good for us. And so it's these little radio buttons down here, and I can experiment. I can see, yep, that is going in the positive Y direction, but we wanted the negative Y direction. So we're going to hit that. It flips it, right? You see which way the arrows go. And we had a load of 3.5 newtons. So right here, this is the model, and this was the problem. You can see that the problem didn't represent that 10 millimeter very well. And we can go to mesh now, and we could just accept the default mesh by hitting right clicking and hit create mesh. When we go to create mesh, you can see there's a slider for how coarse and how fine the mesh is going to be. We'll just hit reset and keep it right here, and then we can, when we get to this, we could kind of judge what our mesh looks like, right? Kind of getting an idea of what this, what our results, or what the size and shape of the elements. They look pretty good, right? So we can go to the back of the top and hit run. And if it takes a long time, we can actually see a convergence plot. The default here is going to be for stress. We want to go to displacement, and I'm running out of time. I got to go upstairs here in a second. So I'm going to go to displacement. I'm going to go show that, right? So now it's showing us, and by the way, it's giving us an exaggerated view of, let's see if I can, no, it's not going to let me show it. All right, so up here in the right-hand corner, if I could get rid of some of this information, it'll tell us, yeah, I can just barely read it. It's 13.6 times the actual displacement. So the displacement is a lot less than what's being shown on the screen. But I want to go right-click this and go to Edit Definition, or actually I could do any of those top three because all three of them are represented by these right here. So I'm going to change my first under definition. I'm going to change the displacement in the Y direction because that's the only thing I measured. I'm going to keep it as millimeters, but I could change it the units in this. You can see here's where our deformed shape is. We pick the automatic. You can see it's 13.19. You could go to true scale, or we could define one. We could also, if I go over to settings right here, I can also pick superimpose the undeformed, the deformed shape, right? The model on the deformed shape, and you could change how thick or thin that's going to look onto the thing. So I might want to keep that automatic on there so I can actually kind of see where that's located. And lastly, in the middle one, there's a whole lot of stuff going on. We could put the show max annotation right there, and that actually shows us what the maximum is going to be. So that's one way that we could find the results. And you can see that we have 3.708 is our maximum. We can also change what the scale is down here. We could change what some of the numbers are, and I'm going to emphasize that you do that in a lot of other stuff. But right now, we got what we want, right? So things are in millimeters, and for whatever reason, they're showing us the oh, that's the maximum deformation. Wait, let me edit this again. Remember, it's negative, right? So we actually need the minimum. Sorry, we'll put the minimum on there, and it went out way the hell up there. All right, so I don't know why that happened, right? So if we had the, I don't know why it's doing that to me. I can't move this. There you go. I can move it now. Okay. And I got to go to the ASME meeting, so I'll be right up there in a second. But anyway, we did a pretty good job. All right, so it predicted in the previous one it was going to be 3.77 millimeters, and we got 3.7. What would happen if we were to create a mesh and run? So I'm going to hit the mesh and run thing here, and it took the default right in there. I hit that show again. I got to go. So I'm going to create a mesh, and what would happen if I just ramp it up all the way to the side right there? And we're going to get really tiny mesh right there. The elements got much smaller. I'll hit run. Let's see if it takes a very long time to do. Like you could see a convergence plot like right down here sometimes, so you can see the convergence. Well, see, it didn't take very long, but we'll show a convergence later. But anyway, that didn't actually help my my results. It got close though. So that's it for this video, and we will pick it up in maybe another video, I think.